Hi, so today we're building a music engine and a guitar tool in bevy. So for context, I really like the blues and I like improv stuff on the guitar. But a lot of times doing these things require you to remember and recollect a lot of music concepts at the same time. For example, when you're jamming around to a song, you need to know what chord you're in right now and what chord with in context of the scale it is and what notes are around that chord on what you can access. So the idea here is to build a tool that gives you some visual cue on what paths you have available and which direction you can go. So this can help you explore more more musical dimensions on the guitar. I've also been trying to understand clean architecture from the blog by Bob Martin. So I'm going to try to build this library slash application in as clean of a architectural pattern as possible, and I'll explain what that means. And also, type-driven development is a very popular way to build software in Rust. So this kind of is going to be a heavily, strongly typed music domain system that can be extended into an application and then a bevy application. So the MVP for the idea is you get a UI with a fretboard, then you pick a scale and a key, and then you can pick a chord progression, you can pick a tempo, and the tempo is going to decide with the chord progression what chords are going to be played when. And then when you click play, the scale is going to show, okay, what notes are in the scale and then what chord is currently playing, so that highlight those notes in particular, and also highlight what degree of that scale this chord is. So how do we cleanly design this application? The goal is not to like blindly follow the four-layer architecture of a clean architectural pattern, but to keep the principles in mind and build your crates around it. So for this, we are going to have three main crates. The theory is going to be the domain crate that defines those music theory types. It should only contain pure music ideas that you can express in a music sheet or a guitar tab. Anything that cannot be expressed there should probably not live in theory. Then we are going to have the app. The app itself is going to be where the uh, kind of business logic of this application goes, but it should also not use any dependencies from like bevy or any infrastructure layer. It should be a very clean dependency graph for app depending on theory, but it can have some basic things. For example, if I need randomization, and it has some like random library. And then finally the presentation layer, which is going to be the bevy UI layer. This is where there should be minimal logic. What app does is it takes a state and it gives you a visualization of that state in a struct, and the presentation layer should just visualize it. For disclaimer, I am not completely anti AI, and for this app, I tried to pretty much not use any LLMs for theory and app. But for bevy UI, I'm not a UI person, and I used LLMs quite a bit to help build a nice, appealing UI. And I think that's how I feel is a good combination of using LLMs. Okay, so the theory crate. The point of this crate is to define the core musical ideas. Here, there's going to be two major types of expressions we have: a concrete expression like a note or a scale degree, and then the relative measurement of these. So, for example, we'll have 12 notes, and then how do you measure between two notes is semitones, similar as scale degree. And for the other type is going to be a recipe on how you can build something and an instance of it. For example, a scale type, for example, a major scale or a minor scale, and then the instance of it is going to be when you attach a tonic to it. So, for example, when you attach a C to a major scale type, it becomes a C major scale. We'll see how the other types work in similar way for the other pattern. So, like starting with, for example, a note. A note is going to be just 12 notes from A to G sharp, and a semitone. A semitone is how you measure between two notes. So, for example, the distance between A and A sharp is one semitone, and A and G is like 12 semitones and 11 semitones. And then you have some functions that can transpose up. So for example, given a note, move it up five semitones, and then you get whatever the five semitones up for it is. As you can see, the semitone itself does not restrict to 12, because you can go like 200 semitones up from some note, and sure, it's just a modulo of the 12, but it's a concept you can express if I attach a audio frequency to it. The second one is scale degrees. So we are only going to deal with diatonic scales here, in which case there is only seven notes in a scale, and a scale degree tells which index into the scale you're currently looking at. And the interval itself is a scale degree with an altercation. So, for example, you can have the third degree, and then if you alter it by -1, then you get a minor third, or like a fifth degree that you can alter by -1, like go down one semitone and you can get a diminished fifth. So that gives us a really nice helper util on the intervals, which is semitones. What semitones can tell you is what is the number of semitones between any interval and the root. For example, major third is going to tell you you go three, like from 0 to 2, that's going to be four semitones, right? And minor third is going to be four semitones minus one offset, that's going to be three semitones. This is going to really come in handy as we build scales and chords. So as you see, the scale type is going to be just an enum. Diatonic means seven notes, and we are only going to work with seven note scales for at least now. So how you build a scale is you just have seven intervals. And as you can see, this is a purely compile time construct. The const function there tells you can compile this function and run this function during compile time. The good thing that this gives us is our program is probably not going to crash randomly because we defined a scale wrong. Of course, this still can define a wrong scale. For example, a major scale can, let's say, accidentally have a minor third, which makes it a wrong scale, but that doesn't make the program crash. And we can also add more validations on top to make this nicer, that I need to think about how to design this type better. The scale itself, like I mentioned, was you have a scale type and you attach a tonic to it, and that gives you a instantiation of the scale, for example, a C major scale. And you can get all the notes from a scale by going to an interval of the scale and then seeing how many semitones there are and move your root up to those many semitones to give you a note. So that's how you can get all the notes for C major. So the chords are very similar to scales, where you have a enum for chord type, and then you have intervals that are defined for each enum. Also, a good thing about Rust is when you have these match statements that I have to have an implementation for each type. So now if I like create a new chord type, I will have to create a match for it. So that makes sure I don't accidentally break this. Sometime I add the new variant to the enum. Now, how do you build a triad from a scale? Because each scale at each degree has a chord defined by three notes. In music theory, how this works is you take the three alternative degrees and you take the notes from them, and then when you combine them and you match them against a formula, you find out what chord it is. In this case, how we do it is we just take the three intervals, then we take the root of those three intervals, like the first interval like that we are starting with, and then we calculate the semitones distance from this interval to each other, and then we just pattern match it on the chord type. Then that gives us if it's a minor, major, or diminished chord. Chord progressions are a harmony that is that can be for now just a single chord, but for extensibility, on harmony we can add a seventh or a ninth or something like that to make more complicated chords. And a chord progression is just a list of harmonies. So then we have to define the guitar domain type. Guitar itself is going to have two simple core constructs, a guitar string and a fret. And using the string and a fret, we define a tuning on the guitar, like the open tuning. And then given a string, fret, and tuning, we can find out what notes exist on what frets and what all frets are there for a given note and stuff like that. Um, and this is how you're going to calculate how you find the note at a fret. Given a guitar string, you know the tuning, and then if you go up like the fret number of semitones from the open string, you find what the note at that string is. And now we come to the second part. This is the core app part. App has three things. It has a state, it has a list of commands that you can give to the app that mutates the state, and it has a view function that returns an app view, which is just a presentation layer that any infrastructure or presentation layer takes and shows it to the user. The app state itself is pretty simple. This is the information you need for the app. In the current state of where I am on this application, it's going to be the tonic, the scale you need, the chord progression, and focus is enum to see the scale degrees or the actual notes. It comes in handy when you're trying to stick to a scale and see what position you're at. The app commands are simple. Then in that case, you want to select a tonic, you want to update your chord type, scale type, etc. And the view is just like I would think as a JSON output of a REST API. It just gives you a fully readable struct that you can use to render out your final UI. And the app flow itself is pretty standard. User gives an input, bevy takes that input and dispatches an app to the command. The command changes the app state, and then bevy asks for a view from the app, and then bevy renders this view. Now we come to the bevy part. The bevy part is the presentation layer. This is where I took the most help of a UI. So I'm going to just skip over a lot of what the UI aspect of it did, because it's a huge, long boilerplate code building out the fretboard and stuff like that. But we start with just building a very basic app where we have the app resource. The app resource is which contains the instance of the app that has the state, etc., and a way to dispatch commands to the app. And then we just, using some LLM magic, build a basic fretboard. Um, I'm not super sure if I'm going to post the code for this, but if I do, then this will be visible to like just a bunch of boilerplate code. And then we use each UI to add a lot of selectable components. The basic flow of how this works is you show components, you show controls, and then when a control changes, you dispatch a command to the app, and then you repeat this loop. And then that gets us to the final app. This is kind of what the app looks like. You can select a key, you can pick what kind of key you want, and then you can pick what degree chord of that key you want to look at. And also, this is where you can add new chords, and then you can just start playing the chord progression on given a tempo. And that will cycle through all the chords. And if you see, these groupings are going to be where your chords first, third, and fifth are, and then you can see the relative notes that you want with respect to that. And yeah, so that's it. I'll have a link for the app in the description and you can try it out. And there's going to be a follow along blog explaining how I use this app and probably some improvements to the app.